Okay, we're going to do another maybe slightly harder L'Hopital's rule problem. I've written it down here. Now, this is going to be a natural log problem, so we're going to use the natural log to solve this. You could also use the natural log in a different way, but I'm a fan of taking the natural log of both sides. The only thing that you have to remember when you do that is that you convert it back to the original when you're done. I'll explain what I mean when we get there. So we're going to check which indeterminate form we're dealing with here, if we're even dealing with an indeterminate form, by substituting the constant that x is approaching. So if we do that, we will find that it's 1 minus 0 to the 1 over 0. What does that mean? It means that we have 1 to the infinity, because 1 over 0 is infinity, right? That's why it does not exist. When a limit is infinity, it doesn't exist, but it's a different type of not existing, if that makes sense. So that means we are dealing with an indeterminate form that we can solve with L'Hopital's rule. So let's try to solve it with L'Hopital's rule. Well, can we even apply L'Hopital's rule yet? No, not yet. I don't think so. What we want to do is we want to take the natural log of both sides so that we can get this to be a fraction, right? Because in order to use L'Hopital's rule, it has to be in fraction form. So we're going to take ln. We're going to let 1 minus 2x to the 1 over x equal y. Okay, so now we're going to take ln y, and we're going to take ln of 1 minus 2x to the 1 over x, and just to be clear, we're not taking the ln to the 1 over x. I'm going to put an extra bracket there, okay? So now we're going to take this exponent down, because if you recall, the log base a of b to the k is k times log a b, right? So we're going to get ln y equals 1 over x times ln of 1 minus 2x. Well, great, because we can just stick this ln 1 minus 2 over x on the numerator here, and we're going to have our fractional form. We're going to have ln of 1 minus 2x over x. And then this is going to be our f of x, and this is going to be our g of x, and we can apply L'Hopital's rule. So let's apply it. So let's write the limit and everything. Limit as x approaches 0 of ln 1 minus 2x over x. Now, remember that we're taking the entire thing, and remember that we need to convert this back to its original form, and that this is the exact same thing as 1 minus 2x to the 1x, right? As long as we remember that we've taken the natural log of y, and we need to fix that when we get the answer here. So the derivative of ln 1 minus 2x, let me just write this here. The derivative of the numerator and the derivative of the denominator, f prime of x is going to be 1 over 1 minus 2x times minus 2, because there's a chain rule here. Obviously, the outer function is ln x, and the inner function is 1 minus 2x. So that's going to actually equal, that's going to equal negative 2 over 1 minus 2x. Negative 2 over 1 minus 2x. Can I simplify that any further? Yes, actually it's not going to matter, because when I take the derivative of x, that's going to be 1. That's going to be 1. So this is just going to be this over 1. So we're actually going to end up with limit as x approaches 0 of negative 2 over 1 minus 2x. And then if we substitute 0 now, we end up with negative 2 over 1 minus 2 times 0, which is just negative 2. But that is not our final solution, and the reason is that we still have ln of y over on this other side, right? This is ln of y. So in order to get our final solution, we write ln of y equals negative 2. Well, do you know how to convert this back? This is log base e of y equals negative 2, and therefore we know that e to the negative 2 equals y. So y equals e to the negative 2. That is our solution. That is our limit. Our limit is e to the negative 2.